We were trying to solve some problems in the last class, what I called exercise 1. We shall continue with that exercise, and the problem is 1.7. Possibly I have covered it, but nevertheless I shall go through it quickly. The idea is to estimate the RB, the conversion factor from horizontal radiation to the tilted radiation, for a collector with a slope of 5 plus 15 degrees or equal to 5 degrees or 5 minus 15 from horizontal, south facing in New Delhi location at 9:30 a.m. on March 21st, 23rd and December 23rd. So, these dates were chosen. The first one is the equinoctial day, declination is 0, and June has the maximum positive declination and December has the maximum magnitude wise negative declination. So, in general we want beta equal to 5 plus 15 degrees and beta is equal to 5 and beta equal to 5 minus 15 degrees. So, you can find out that the slope is plus 15 degrees. I can expect this to be a better orientation for winter in general, or let us say November, December, January, because the sun's rays are pretty much lower, and if you have a higher slope, then they will be near normal incidence, whereas this will be favorable for summer. A beta is equal to 5 is sort of a compromise for the throughout year best collection, which we shall do or calculate little later. And it is given for Delhi phi as 28.56 degrees I think, and time 9:30 corresponds to omega of minus 37.5, and March dates are plus or minus, does not matter, delta is 0, and June delta is positive 23.45, and December 23 you have declination of minus 23.45. So, I will go through these numbers quickly, so that we can conclude something out of this exercise. So, RB for a south facing surface is the angle of incidence for the south facing surface cos phi minus beta cos delta cos omega plus sin phi minus beta sin delta over cos phi cos delta cos omega plus sin phi sin delta. First, we take up March with delta equal to 0, and if beta equal to 5 plus 15 degrees, 5 minus beta is minus 15, and RB is, I have done the calculation last time, 1.09, sorry, 1.09. So, this is for beta 5 plus March, and so you can fill in the numbers and find out that they are okay. And second case, so this 1, 2, this I may call it A March. So, beta equal to 5 and RB turns out to be 1.09 0.09. I am just wondering whether it's the same. Okay, we can check up that algebra a little later, or sorry, arithmetics. Yeah, for different reasons it will turn out to be the same. You can just check, because delta being 0 or phi minus beta being 0. And then you have the third case, June 23rd, delta is 23.45, beta okay. So, when you have got, let me repeat, I am sorry, when beta is equal to phi, your R B is 1.138. It cannot be the same as beta is equal to phi plus 15. The third case is beta is equal to phi minus 15, for which R B is equal to 1.09. So, that phi plus 15 and phi minus 15, they give you the same R B factor in the month of March, because declination is 0. This will not happen if declination is non-zero. Okay. So, we go to the next date, June 23rd, and declination is 23.45. First case being beta phi plus 15 or phi minus beta equal to minus 15, and R B you will have a low value less than 1.725. We have gone through these numbers, and I am just repeating for some reason, which you will come to know towards the end of this problem. And for the second case of beta is equal to phi, you have R B slightly better, 0.8785. Please go through the arithmetic calculation, a simple relation, and which we have done in detail last class. So, you can again check it up, and you will find if there is a difference. Qualitatively, I do not think there will be much difference. Phi minus 15, and this gives rise to R B 0.9717. One thing that has come out clearly, compared to March 21st, June 23rd has poorer R B for these orientations. And if you go to December 23rd with a declination of minus 23.45, for the first case of phi minus beta equal to minus 15, you will have R B 1.79, and then if the second case beta is equal to the latitude phi, you have R B is equal to 1.623, and if you have third one phi minus beta equal to plus 15, then RB is 1.34. So, all these calculations we have done, just it is essentially for continuity. And if I set myself up a table in summary, the time is 9:30 a.m. location New Delhi. So, latitude is 28 degrees 34 minutes north, and day we are considering March 21, then June 23 and December 23. So, you have got beta 5 plus 15, beta equal to 5 and beta equal to 5 minus 15 with the corresponding values of 1.09, 1.138 and 1.09 and 0.725, 0.8785 and 0.9717 versus 1.79, 1.623 and 1.34. What comes out distinctly is that in tilt factors for negative declination are higher than those values for positive declination A. And this is because delta is 0, 5 plus 15 and 5 minus 15, they have the same values, right. Basically, what it means is, if this is the solar collector and if this is the outer normal. Now, 5 plus 15 may have a ray like this and 5 minus 15 may have a ray like this, but still this theta remains the same. Consequently, you have the same answer for RB, or whether beta is 5 plus 15 or 5 minus 15. So, in two dimensional view, it looks like that there is a ray in one line, but that ray could be a pencil along a cone describing the same angle. And of course, 5 plus 15 and December negative declination, you have the highest 1.79. So, if you have a certain horizontal radiation, even if it is 1.5 times, 1.2 times the December value, you have a pretty good inclination factor if you choose the right slope. So, we will go to problem number 1.8. So, what is the extraterrestrial radiation on a horizontal surface I0 at Chennai, whose latitude is 13 degrees north, during the hour 10:30 to 11:30. Now, I shall go back to the previous problem after finish this. This time reminded me of something that I can tell you. So, declination for this Chennai will be 23.45 on that day, rather any location, sin 360 times 284 plus n by 365, that equal to minus 20.9, because it is January 15th, n is equal to 15. It is almost the mean declination. So, I0 for 10:30 to 11:30, my omega 1 will be minus 22.5 and omega 2 will be minus 7.5 degrees, right. 11:30 corresponds to minus 7.5, half an hour before the solar noon. This is 1.5 hours before the solar noon. So, it will be minus 22.5 and minus 7.5 as per our convention. So, I 0, I will repeat the formula, so that you will remember little better. So, 12 into 3600 by pi times the solar constant G S C times the variation 0.033 cos 360 n by 365 times cos phi cos delta sin omega 2 minus sin omega 1 plus 2 pi omega 2 minus omega 1 by 360. So, this omega 2 and omega 1 are degrees. Since I am using pi by 180 or 2 pi by 360 as the conversion factor, times sin phi sin delta. So, this is if you this will be 12 times 3600 multiplied by 1353. This is the value I use for GSC, 1353 watts per meter square by pi 22 by 7. So, it goes to the numerator multiplied by 1 plus 0.033 cos 360 into n is 15 by 365 times cosine phi cos delta times sin omega 2 minus sin omega 1 plus 2 pi into omega 2 minus, which becomes plus 22.5 omega 1 by 360 times sin phi times sin delta. Okay. So, you can check up each number and pause your videos and check up whether the formula is written or not, and then you can calculate. So, if you make this long calculation, answer will be I 0 4.0747 megajoules per meter square hour according to our notation. Okay. So, this is what you will get. Now, we are asked to calculate what is H 0 for January 15 New Delhi. Okay. So, this I need the sunset hour angle omega s will be cos inverse minus tan or 13 tan delta, which is minus 20.9. This is the location is Chennai. So, 13 degrees. So, sorry. Okay. So, you have got this omega s is 84.96 degrees. So, you can understand that this is January, but at a low latitude. So, you almost have 90, but less than 90 it should be, and H 0 will be 24 into 3600 multiplied by solar constant 1353 by pi 22 by 7 times 1 plus 0.033 cos 360 into 15, that is n, by 365 multiplied by cos phi cos delta sin omega s plus twice 22 by pi times omega s by 360, 2 pi by 360 sin phi times sin delta. So, this comes to 30.205 megajoules per meter squared day. So, you can check up from standard textbooks the extraterrestrial radiation tabulated at intervals of 10 degrees, maybe 10, 20, 30, 40, and by interpolation between 10 and 20 you can check whether this is okay or not for Chennai, which is at 13 degrees. The name is location is Chennai we are choosing, otherwise what really matters only is the latitude 13 degrees and the day that we have considered, not the physical name of the location. So, we will go to problem 1.9. This is if the horizontal daily radiation in the above problem has been measured to be 19.8 megajoules per meter square a day, what is the daily clearness index? 1.9 given as per our notation H equal to 19.8 megajoules per meter squared day, and you are required to calculate daily clearness index. Capital K T, and capital K T is H upon H 0, right. From 1.8 problem, H 0 is 30.205 megajoules per meter squared day. So, your clearness index K T will be H by H 0, which is 19.8 by 30.205 equal to 0.655. So, it is not that it is a great calculation or problem, but the problems in your course or in reality or in the exams can be formulated in different ways. For example, without 1.8 and given that the global radiation on a horizontal surface 19.8, what is the clearness index? The whole idea is you will have to calculate H 0 also to get the clearness index K T. So, now we go to the next problem 1.10. So, if the global radiation on a horizontal surface has been found to be 1.8 megajoules per meter square hour for the hour 10 to 11 at a location of latitude 40 degrees on January 15, find the hourly clearness index. Like I was mentioning, this problem has been modified to take care of the hourly factor rather than the daily. So, as per our notation, we are given I equal to 1.8 megajoules per meter square hour. The day time is 10 to 11 a.m. These will come to hour angles at a location of latitude 40 degrees and day is January 15th. Okay. So, the formula is, first I should find out I 0 should be equal to 12 into 3600 by pi GSC times 1 plus 0.033 cos 360 n by 365 times cos phi cos delta times sin omega 2 minus sin omega 1 plus 2 pi omega 2 minus omega 1 by 360 times sin phi sin delta. Same formula we have used. So, the latitude phi is 40 degrees and delta, it is the mean declination for the month of January, is minus 20.9, or you can calculate delta is equal to 23.45 sin 284 plus n by 365, whatever it is multiplied by 360. Check. So, declination for January 15 is minus 20.9. You can plug it in this. If this formula is slightly wrong, you can correct it. I think it is okay, right. So, and omega 1 will be 30 degrees minus and omega 2 is minus 15 degrees. So, the time is 10 to 11. 11 o'clock will correspond to minus 15 and 10 o'clock will correspond to minus 30. So, omega 1 is minus 30 and omega 2 is minus 15. So, I 0, if you plug in all these numbers, comes out to be 2.167726 megajoules per meter squared hour. So, we are also required to find out the clearness index. So, and I guess this is okay even if you say 2.17 megajoules per meter square hour. In fact, my professor used to deduct some marks if you give too many decimals, because there is no way of measuring so accurately, simply because the calculator is giving, do not put 8 to 12 decimal places. For solar energy 2 or 3 are more than adequate. And your K T is your I 1.8 by 2.17. Please calculate this. I just thought I calculated I 0 and forgot to do this simple division. Okay. Now, we shall go to problem 1.11. Estimate the ratio of beam radiation on a surface tilted 45 degrees toward the south to that on a horizontal surface if located at a latitude of 40 degrees on March 1st A at noon time and B at 3:30. So, it is a straightforward calculation of RB, right. So, this is going to tell us something. 1.11 latitude is 40 degrees N, slope beta is 45 degrees N, March 1, and at noon and at 3:30 p.m. So, declination is 23.45 sin 284 plus 31 plus 28, because this is March 1st, 31 days for the month of January and 28 for the month of February. So, it will be, I can even put 29, does not matter, upon 365 times 360. I think in the previous example I was forgetting this 284, but you can correct it. So, 23.45 times sin 33830, which comes to minus 8.6 degrees. This is quite okay, because this is March 1st. Before the equinoctial day, it should be negative, and we got a reasonably low negative number, minus 8.6 degrees. And at noon time, which means omega is 0 for noon time. So, my RB will be cos phi minus beta cos delta cos omega plus sin phi minus beta sin delta upon cos phi, which is 40 cos delta times cos 0, which is omega, plus sin phi sin delta. This comes to 1.538. Now, you will find that beta is close to 40, omega is of course noon time, the best south oriented surface, and the declination is pretty low in the sense that it is close to equinoctial days. So, we found in the Constantine collectors phi minus beta is equal to delta is an optimum orientation. So, similarly here you have got phi pretty close to beta and pretty close to the equinoctial day. So, you have got a fairly high RB at noon time. So, now the next one is omega 330. which comes to 52.5. So, 1 o'clock is 15, 2 o'clock is 30, 3 o'clock is 45 plus 7.5 for 3:30. So, R B same step, cos phi minus beta, cos delta, cos omega plus sin phi minus beta sin delta upon cos phi cos delta cos omega plus sin phi sin delta. This is 1.88. So, the RB factor is pretty high at this omega is equal to 52.5. In fact, it is more than 1.538. So, please check the calculation once again. It may be quite right, but I believe at 3:30 it may not be higher than what it is at the noon time, unless your 10 minus 45, that phi minus beta is making a different situation. Okay. All right, you just check it out. Or I also have a number here, 1.66. So, I will give you a clarification in the next class which one is the correct one, either 1.66 or 1.88. Okay. So, from these exercises, what we learnt is calculation of extraterrestrial I0 or H0 or the declination for a given day and solar time and the angles of incidence for different orientations and clearness index on a daily basis or a hourly basis, and then the RB factors. So, which we found a pattern that in general, if you appropriately orient your collector, RB will be high in winter, and of course, clearness index has something to do with the solar radiation as received. Similarly, angle of incidence will be favorable in December when RB is high. A declination, we know that it changes negative to positive to negative to positive from January to December, and I0 and H0 are the measures of the extraterrestrial radiation over a hourly time scale and a daily time scale. Regarding the angles and RB, I was mentioning RB we calculated at some omega, right, 10:30 or whatever it is, say at. So, we have been emphasizing that this RB for the hour 10 to 11 can be calculated at 10:30. Check 1 value at 10 o'clock, 2 value at 11 o'clock, and compare with the value at 10:30. Is it? sort of a linear average or approximately average of these two values at 1030. The third thing that you can do is calculate by using the formula omega 1 to omega 2 I 0 R B d omega by I 0 d omega, which will ultimately turn out to be integral omega 1 to omega 2 of cos theta d omega by integral cos theta z d omega omega 1 to omega 2, right. Like for a day, if I do for an hour in the interval omega 1 to omega 2, I will get the weighted averaged R B factor, and we would like to compare what will be the difference between this weighted average and the value at the midpoint of the hour, right. I have no clue to this difference, but you can calculate simply as if it is a day, the 2 times being omega 1 omega 2 instead of twice of 0 to omega s, and here also omega 1 to omega 2, right. So, you calculate the 3 values at 10 o'clock, at 11 o'clock and at 10:30, giving the corresponding values, and you check, of course, obviously the value at 10:30 will lie between 10 and 11 o'clock, and how far it is from the average that you can see, and make an exact calculation between omega 1 to omega 2. So, that this will give a estimate of error for the hourly calculation. Okay. So, these are the exercises which we can do, and as some sort of a homework, you can do calculate one H 0 for phi 0 to 90 for the 12 months, let us say H 0 bar. Okay. So, that it is simple. 2 H 0 y bar equal to summation of H 0 bar of each month upon 12 I equal to 1 to 12. So, that you will have an idea with the formula that we have given how much it is off. And third thing you can do is you can calculate, I have already said that omega SR, omega SS for different phi, beta, delta and gamma. Okay. 4 tabulate R B and R B bar, that is the monthly average or the daily. This, let us say, only the delta equal to delta mean for different phi, beta, delta and gamma. So, if you do these exercises, it almost covers all the formulae we have done in the first 3 to 4 topics of lectures, which we have covered through the problems. Thank you.